Okay, so let's start. Thank you for joining today. It's a Friday to get on stage, so it requires extra effort to join. So today's our first really esteemed, esteemed seminar series, and we are co-organizing it with SAIS. So we'd like to thank SAIS for hosting the event. A bit of logistics, because we are hybrid and the logistics are a bit complicated. Please do not ask any questions during the talk. Hold your question for the end. Unless there is a burning, clarifying question you absolutely have to ask, that's okay. But in that case, we use the mic so that people that are on Zoom can hear the question. And then if you can keep most of your questions for the end, then again, we'll have the mic go around so that you can be heard online. Let me thank all of the people that contributed to organizing the event, the Hariri staff, the SAIS staff, and also Zili Wang, that was a student host. Thank you. And a few things about Elad Hazan. I think it's very appropriate that we start this seminar series with Elad. He's very well known. He's a professor of computer science at Princeton. He comes from the optimization world, even though he is very much interested in control, as you are going to see. He is a co-inventor of the AdaGrad algorithm that is used quite a bit in machine learning, in deep learning. He has written a recent book on online convex optimization. He's one of the pioneers of online optimization. He has received a number of prizes, the Bell Labs Prize, the IBM Goldberg Best Paper Award twice. He has received the European Research Council grant, again twice, a Marie Curie Fellowship, and then twice the Google Research Award. He has been a program chair for COLT in 2015. He's a co-founder of a company that after a year was acquired by Google, and he's now, while at Princeton, the director of Google AI, which is a small Google outfit in New Jersey, very close to the Princeton campus. So with that, Elad, the floor is yours.
Thank you, Yanis. Thank you so much for the kind words and the invitation. Can you all hear me in the back also? Good. Yeah, as Yanis kindly said, my name is Elad Hazan. I'm from Princeton. Let me override him on one small thing. If you have questions, please ask, because otherwise it's not so nice for me to put in front of the audience. What we'll do for the people back home, I'll just repeat the question. So there is a question, I'll repeat it, and then this way we can, because I really prefer audience interaction. Oh, we cannot see my slides. Can we, how do I? I will be talking about work which I have been involved in the past, I would say 3-4 years. It was a lot of co-authors. Started with Naman here, with my former students now at Google AI Princeton, and Shini also there, and Sham, the professor at Harvard today, Paula, grad student at Berkeley, Udai, my student, and you know, I'm not going to name everyone. A lot of people, so many of them don't appear here. Their names appear here below. By now, we've collaborated with Annie, who's a robotics professor in Princeton, Naomi Leonard, who's a control theorist in Princeton. So many collaborators. These are the initial group, I would say, that we collaborated with, and by now there are more. It's a growing community looking at the intersection of learning to control. Here is a setup that I have a video. Unfortunately, I cannot play it due to internet, but this is a setup we have in our Google lab. It is a ventilator rack. So this is something we got interested in during COVID for obvious reasons. Ventilation is very important to keep sedated patients breathing and alive. In this rack, we have a set of ventilators that we built, and this here is a lung. This is an artificial lung connected to the ventilator. And we studied the control problem of ventilating the patient, sedated patient. The goal in this problem is to maintain a healthy breathing form as determined by a clinician. So the blue line here represents the pressure inside the lung, and the dotted line is what the clinician would like to see on their screen. So we started looking at this problem from a learning perspective, and I would like to keep this in mind for the rest of my talk because I think it's a very illustrating problem for what I'm going to talk about. There is an underlying dynamical system, very complex one, right? So we have the patient with the lung and all sorts of issues obfuscating the breath. We have a tracking problem here that we would like to track this waveform here. And we have very limited observation. All we can measure is a scalar. So one point real valued pressure, and we can also, our control is also a scalar. How much do we open the oxygen or air intake to the patient? So seemingly very simple, 1D input, 1D output, but very complex and very important problem underneath. And this represents an agent interacting with the environment, receiving a signal and contributing back an action or a control. At that time, and I think the conception was that in many ways control, which is a classical field usually studied in ECE departments, and reinforcement learning, which is usually studied in computer science, discrete applications, and so on, are very similar and essentially the same. So this talk is actually about how they are different. What I would like to do is talk about how we can model an environment in a nice differentiable way and be able to use robust gradient-based methods and to get provable finite time guarantees that are currently out of reach of full reinforcement learning for a good reason, for a good complexity theoretic reason. So what I want to cover, I'll be happy if I cover a single basic result, which is called a gradient perturbation controller. It's a new method for control. It has a different philosophy behind it than things maybe you learned in control theory, such as optimal or robust control. And it is much more akin to stuff like Ashok and Francesco are doing in the online learning world. So if I get that across, wonderful. And if I have time, I'll show some demonstrations and give you pointers to more sophisticated results that we have been working on since. So this online control framework lies in the intersection of several paradigms. One of them is model-based reinforcement learning. I'm guessing all of you in the audience have some kind of background in model-based reinforcement learning. Online convex optimization, which is a technique for iterative decision-making based on optimization. And convex relaxation, which is a technique from optimization on how to take a problem which is the naive formulation of it is hard and relax it to make it polynomial time solvable. An example is for people that know Lasso, right? Lasso from statistics, try to learn a sparse predictor. If you try to learn a sparse predictor in a naive way, this is NP-how. You cannot really learn a very sparse, like 4-coordinate predictor. But you can relax. You can do an L1 relaxation, like the Lasso, becomes polynomial time solvable, convex, and that's kind of the third tier of this framework. I will start by saying a few words about online convex optimization at the risk of boring some of my colleagues here that are experts, but nevertheless, for the rest of the crowd, this is a decision-making framework in which we have an adversary and a player. Every iteration, the player chooses a point in a convex set, and adversary reveals the convex cost function and suffers a loss. And this is repeated again and again and again until we have a total loss. The measure here, this is not a statistical framework, this is an adversarial framework. I just had discussion with some of my colleagues. When do we have When can we justify a purely adversarial scenario? In this talk, I will justify it. No, it's not statistical. So when you're controlling a ventilator for a human, this is not a statistical situation. You cannot make statistical assumptions about the behavior of the general population, but have to adapt to the particular patient. In this situation, we don't, like classical machine learning, we don't measure risk or but something much more akin to excess risk. It's called regret, and that's the total loss minus the difference between the total loss of the player and that of the best fixed decision in hindsight. It's called regret. You have a question here? And we would like the regret to go to zero as time goes to infinity. This is the desiderata of the setting. And it's a very robust framework. There are many examples of convex set of interest. For example, you can model linear regression or short, but this is particularly nice. You can model all passes in a graph by a convex set, even though there are exponentially many passes in a graph in the representation. The polytope that represents all of them lies in low dimension and has few constraints. It's called the flow polytope. So a nice thing, I need it here like mathematically, the nice thing is that you can represent by the language of optimization complicated discrete structures very efficiently in low dimension. That's what the language allows you to do. Many other examples exist. Today, the decision set that we are concerned with is a class of policies for control that take an input and output a control, for example, the pressure of the ventilator. Why is online convex optimization important? So, as opposed to statistical, why am I kind of telling you about it? It's very important for control because we have a non-stochastic, many times adversarial, many times multi-party setting. So statistics doesn't give you the guarantee you want. You want something which is more fine-tuned. It's by now very well understood. There are many algorithms and techniques developed. Here is the most basic one, which I will use. It's called online gradient descent. You've seen it in some variant of them or another. This is the adaptation to the online world. In this setting of online convex optimization, right, we have iteratively these functions coming. They are chosen by an adversary. What this algorithm does, it chooses the next point according to movement of the gradient of the previous function, even though the next function can be totally different, maybe counterintuitive. You still do that, and maybe you violate the constraints, so you have to project back to the set. So this is an illustration of the algorithm. Is it okay? People have seen this before? Or similar things, right? I guess the counterintuitive fact here is that why is this any good to move in the direction of a function, even though it changes, okay? And it changes in a kind of an adversarial way. So you can show that the regret, this difference between loss accumulated and that of the best decision in hindsight, behaves like square root of the number of iterations, and this is like, that's why it's good. This implies statistical guarantees. If you are familiar with like 1/epsilon squared rates for statistical learning, it implies them. Any question about that? People have seen this before, kind of? Yeah, good. Yeah, so this is a beautiful result in my opinion. Because people have seen it, I'm going to skip analysis, but this slide just serves to show you can do it in a single slide. You can do this woofy kind of guarantee. I like to show it especially to the control people so they will believe me when I go to kind of control that indeed the guarantees are correct. That you can in one slide show that even though you have a changing function adversarially changing, you can get meaningful regret bounds. And the constants are small, constant is 2. And the algorithm is simple and it's efficiently implementable, and there is nothing hiding underneath here in the analysis or the algorithm itself. Good. So by now, there are many other methods for online convex optimization. I've listed some of the algorithms here. They're based on projection-free, Frank-Wolf algorithms, and Newton algorithms, many others. And what I'd like to do next is, if you all believe me that this technology exists and is correct and it's accurate and efficient methods exist, I want to talk about how to use this for control. So part one, basics of non-stochastic online non-stochastic control. And this is the formulation I'm going to be working with. So now this is maybe less familiar to the online learning people, but more familiar to the control people. I have a dynamical system, which is captured by this evolution. So X is a state, think of pressure in the lung or some other parameters of the patient. And they evolve according to some function, some dynamical function. And in addition to the dynamics, we have a control, which is denoted by U. That is the signal that we, the controller, input to the system. And that shifts between state at time t and state at time t plus 1. I'm using here a discrete time formulation because that's what happens on the computer, right? We have discrete time, we don't have any continuous time. And A and B, this is much, in my opinion, simpler than differential equations that you need for continuous time. And there is a noise here, W. So this is how the system evolves. There is kind of diagram here. Here's the state of the system and noise added and control added. At every iteration, we suffer the cost. You can think of it and this cost can be changing. You can think of it, for example, as how much away I am from what the clinician prescribed in terms of volume of my lung. That's going to be the cost. So L2 norm or L1 norm or whatever your metric is. And I'd like to select a set of inputs to the system to minimize this cost. Okay. Yeah. Any questions so far? Okay. Good. Good. So Lyapunov suggested to do the following. So if we have a smooth dynamical system, we can, almost without also generality, if we sample closely enough. So he said you can replace the dynamical system by the Jacobian of the dynamics with respect to the state and the control. And that will give you a changing linear dynamical system, which is given by this equation. So state evolves. Now we don't have this kind of F, but we have matrices that convert state and action to the next state. Yeah. Everyone okay with this? It's almost no loss of generality here, unless I have a non-smooth dynamical system. Good. So I'm going to work with this formulation. And now my question to you is, if I know the system is called the dynamics, or these matrices A and B. Suppose I know them because I have a neural net simulator, or I have equations coming from physics that I studied in AdaGrad or whatever other reason. Can I find the optimal control? Optimal that minimizes the cost. So what is the answer to that? Of course. Yeah, of course I can. I didn't say efficiently, right? I mean, of course I can compute. I can, presumably, if the noise behaves like stochastic or random variable or something, it's a stochastic optimization problem, and I can maybe try all possibilities of use and see which minimize the cost. Yeah, so in principle we can, if we have a stochastic perturbation. This is called optimal control. And here is an example. This is called LQR. It's a very well-known example due to Kalman. Some would say bread and butter of control. So LQR, we have costs. These costs are quadratic. They're quadratic function, convex quadratic functions of x and u. And then, if that happens, what Kalman has shown is that the solution, the optimal control to this, the optimal use, are not only, you don't need to solve an exponentially sized mathematical program, you can actually write in a very succinct form. They are a linear map from state to action that can be written like this. So this is a consequence of the Bellman equation, right? The Bellman equation, solve for it. People have seen this, and you control people have seen it, right? Kind of like you maybe haven't. I mean, I didn't know this before I started teaching it. So you can write like the Bellman equation and differentiate. It's quadratic. Quadratic means that the differential is linear, and therefore you solve a system of linear equations. That's what you did. So this is very nice. well studied also in high dimensions. There are all sorts of non-trivialities here. It's called the algebraic Riccati equation and so on. Good. Yeah, so that's how you derive it. You write the value function, you assume it's quadratic, and by induction you show it remains quadratic if the solution is in there. Yeah, so this is essentially known from the 60s by Kalman. Then you can talk about, wait a minute, what if my noise is not stochastic? There is something called robust control, also known as age infinity. And that says, okay, how about I compute the best control subject to the worst case noise lying in some uncertainty set, some set. It's called robust, coming from robust optimization. So also very rich theory. This is from the 80s, maybe I would say, until today, still actively researched. It turns out that under certain situations, you can even solve this efficiently. These situations mean that the cost functions are quadratic. And then you can prove that the solution is also a linear controller, changing linear controller. This in general is kind of considered to be pessimistic, because what happens if you plan for the worst case noise, then there is no noise at all. So you're kind of left with a very pessimistic controller. Right? Okay, so I would like to go beyond this, and I'm motivated by two things. First of all, I would like something which is more robust. I'd like to be adaptive. I'd like to be adaptive. If there is no noise, I want to do great. If there is super adversarial noise, I want to maintain the guarantees of robust control. But I also want to be instance optimal. So whatever the noise is, I want to compete with the best controller for that particular stronger guarantee. And second of all, which I think is very important, I want to be able to add constraints. And how do we add constraints in machine learning? We modify the cost function. We modify the objective. We add a Lagrangian with constraints. That's a very natural thing to do. So Rockefeller in the 80s says this is a good idea to consider moving beyond quadratics. Like let's say add linear L1 losses, whatever, other loss functions. We use this all the time in machine learning, not only L2. Like there's a variety of interesting loss functions that we shape our goal according to them. Good. So here is a motivating example. I want to fly a drone from source to destination, and I don't know the weather conditions. So, right. So, what does the optimal control says? It says the wind is like a random variable, a Gaussian random variable. It's obviously not good enough. And age infinity or robust control says plan for the worst case noise. But then what happens if the weather turned out to be great? No wind at all. Then I wasted all this energy to fly very safely where I could have done something better. Right? Okay, so I would like to have an adaptive controller that can fly efficient and fast when the weather permits, and otherwise be very careful. And I want finite time provable guarantees, and I want an efficient algorithm. So I want all of these things. And this is now a formulation of the framework that will allow me to do it. I have potentially an unknown dynamical system. Maybe I observe not the whole state, but some projection of the state. It's very hard. There are noises, and these noises are adversarial. They can even adapt to my algorithm. And I would like to minimize cost. Let me, for the remainder of the first part of the talk, just consider like a simpler case that I have full observation of the state. I have this X, I can see it, and I see the state. And I have a linear time variant dynamical system. I'd like to minimize the cost, and every time I choose a control, see the output. Choose a control, see the output. And now I can ask the same question. So suppose that I know the A and the B, can I compute the optimal controller, the optimal sequence of use for my system? And the answer now is no, okay? Because it doesn't matter how much I compute, because I don't know the noise, right? So the optimal controller will depend on the noise that will be revealed after I play my controller, okay? Yeah, point taken. So that's why it's different from optimal/robust control. I cannot even in principle know what the optimal thing is. I have to wait until the end of the whole sequence. Yeah, happy to take a question if there is one now. Okay, so here is a mathematical formulation of what I want to do of online control. Iteratively, I observe this state and select an input, and then I see the loss. And I do it again and again and again. And I want to minimize policy regret, which is the sum of costs versus the sum of costs had I chosen the best policy in hindsight, best with respect to the noise that I have observed. So not best with respect to all noises in the world or Gaussian, to the particular noise sequence that I saw. And this comparator is very challenging because the states here evolved according to some policy that I didn't play. So maybe the states here are going to be different than the states that I actually observed. Okay? Make sense? Yes.
Is this where the need for the model-based component comes in, because you need to be able to compute these counterfactuals?
I'm not going to compute the counterfactuals, the states. Why is there some kind of...
There's a question.
Oh, okay. Okay, first of all, let me repeat for the web. I will repeat your question here, and then they hear me, and then I'll answer, and then I'll take that one. So the question was whether I need a model-based to compute the counterfactual, and the answer is no. I will never compute these ones. I'll just have a guarantee over them. And you can think of the lasso example. When I compute a sparse predictor, or I compete with it, I don't even know what it's NP hard to compute it, okay? But I will still be able to prove that I'm better than it. So the same thing is going to happen here. So that's a good question and an interesting point. Now from the, how do I see the Zoom question?
Just hit the chat right there.
Uh-huh. Doesn't work for me. Okay, I will. One question, I guess, is still projected gradient descent. Answer is yes. Does the adversary select both the perturbation and the cost function? Yeah, great question. The answer is yes. So I'm allowing the adversary to select both the perturbation as long as it's bounded, let's say by one something. Yeah, can choose whatever they want. And the cost functions are also adversarially chosen. And in the full generality, I don't even know them. I only see the cost that I get. Okay. Good. Any other questions? So yeah, this is the setting. If that's clear, already we're kind of half done. I'm happy that people get the setting. It's a challenging setting, right? It's not a trivial thing. And it's different mode of thinking than optimal robust control. Okay. Okay, now I can ask, what is a reasonable comparator class? So I wrote here that I want to compete with the best policy in some class. Why do I need a class? Why do I compete with all policies in the world? So that turns out to be too hard. Even representing the optimal policy requires exponentially many parameters. In the general case, if you have like piecewise linear cost functions, Rockefeller proved that in '87. So I have to restrict myself a little bit, and I want to compete with a set of policy classes. For example, I can think of this first set here, a linear policy. Why is this a reasonable policy class to compete against? Well, we know that for robust and optimal control, when we have a changing linear dynamical system, this is optimal. So if I'm better than that, that's great. Well, it's optimal at least for these settings. And then you can consider all sorts of other things like linear dynamical controller. Those of you from control background, this will be familiar. It's like a Kalman filter type of policy and so on. I'm going to consider this one, disturbance action control. It's the biggest yellow circle here. It is bigger than linear and LDC and so on. It's a convex relaxation, and it's defined by taking a linear function of the past perturbations plus some stabilizing control. So instead of using the state action mapping, I'm using disturbance action mapping. This is in order. I'm just telling this to Yanis before. If you use a state action controller, this will go back into your system, and then in the next state, again, you're kind of optimizing a non-convex situation. It affects your next state and what you did the last time and so on. So it kind of recurses into itself, and you get a non-convex parameterization, whereas this parameterization, as I'll show you, remains convex and nice. But the good thing is that it's bigger. So if I take this history parameter here to be large enough, this class contains linear controllers, and therefore it's a meaningful class. Okay, so here is the first result that I want to talk about. There is an efficient algorithm that has root T regret for this setting, and it competes with all disturbance action controllers. With some, there are some things here that I hide under the O notation that are logarithmic in time and polynomial in the system parameters. Okay, any questions about this? Okay, so this is, again, this is a stronger result than optimal control or robust control because it competes, A, it competes with a larger class, B, it allows any convex function or any quadratic, C, it is, you'll see that it's sufficient, and D, it's the main thing, this holds for any noise sequence, not like some a priori thing, okay? Any noise sequence. Okay, so I'm going to talk a little bit about the analysis and main idea. Unless there are questions about why I want to show this or what's the result itself. No. Okay. So first idea, which also is the main idea, is to do a convex relaxation of the policies, the linear policies. Now, here, suppose I use a linear map from state to action, like K, okay? Then U, the control is a function of K, it's linear, and this I can write down the dynamic. What is xt plus 1? It's A xt plus B ut plus W. The U is also K times xt, right? And that again, I can open up, So I have here a sequence that goes back to the beginning of time with K. K is my variable. That's what I meant when I say that these things compound, become non-convex. So as a function of K, this is a polynomial that is high degree and of course not convex. But notice that all the U's were removed. I only have the W here. That's nature chooses with W. I can replace this matrix here by M. Okay, so I'm now going to call whatever multiplies WT minus I, MI. Just call it that. Call it a different name. This is the kind of the lasso convex relaxation idea, right? I take a bigger class of matrices. They don't need to have this form of A plus BK to the I. They're just called M. That's it. No restriction on them. So obviously, this class of controllers is bigger than the class that can be obtained using this technique here. Okay. Any questions? Okay. Good. So now, because a convex function of a linear function is convex, it's convex in M. This M is a convex parameterization of the of a set of policies which contains all linear policies. In particular, I can compute the best M in hindsight because it's a convex optimization program. It only depends on the W's that I've seen and the cost functions. Any question? Okay. Yeah, this is some kind of schematic to show the relationship between the class of linear policies and that of disturbance action. So this kind of star is, think of all possible Ks, and the different sizes mean that the norm is bigger and bigger and bigger. I can parameterize them by the norm of K. Take a bigger norm, of course, it encompasses the previous set and so on. And this set of M is nice and convex, and when you take a bigger enough norm over the matrices, they contain all the star ones. It's an illustration. Okay. Now step 2. So there was an issue in this formulation that I had here. The issue is that the number of parameters here grows with time. It's not good because I cannot learn number of parameters that grows within my number of iterations linearly. If it grows sublinearly, okay, but if it grows linearly, I cannot. Just from a learning theory perspective, right? There are too many parameters to learn. I can fit too many things. Well, I'm not going to generalize, another way to say it. So what we're going to do is something simple. We're just going to take a number of matrices that is bounded by H. And we can prove that with logarithmically many, such logarithmically in epsilon, this is epsilon close to any stable linear policy. The reason this happens is because this power, a plus bk to the power, it decays exponentially when you have a stabilizable system. There is a stabilizing controller, meaning the whole thing can be less than 1, and then it decays exponentially, right? So if you take high enough power, 1 over the largest spectral radius log 1 over epsilon, this thing going to be less than epsilon, okay? So now we have a constantly many parameters, that's good. You can ask, how do I find the stabilizing controller? This is some other work with my student Shini. And finally, there is another point, which I guess is more subtle. Maybe this is a better fit to you guys, the Ashok and Francesco. So what happens is that I play a policy and I move on to the next time step. Whatever I played the last time affects my cost function because I affected the state, right? So there is some memory thing going on here, right? But that's actually not a huge problem. So we know how to do online learning with memory. We just have a small learning rate. That's it. And then the effects don't compound very rapidly. So there is some subtlety here, bottom line, some subtlety here, which is not very difficult to solve by having a low moving gradient descent. Okay. This is how the final algorithm looks like. Yeah, so you initialize these matrices to be whatever you want, arbitrary, age matrices. And then you use a control. I'm assuming you have this KT, this is just a stabilizing controller. If the system is stable, you use 0, that's fine, you don't need anything. And then you use them together with the past perturbations to create your next control, feed that into the system. Now we observe the next state. We can compute the noise, right? Noise is state minus whatever AXT minus BUT. So I have it, great, and I can build another control and so on. I construct a loss function, which is a composition of the adversarially supplied cost function, and the state and the control is a linear function of the matrices M. That's what I wrote on the board before, right? Summation MI WT on this. It's linear. And I update by gradient rule. There. Okay. That's how the algorithm looks like. Are there any questions about the algorithm? So it's a very efficient algorithm. It requires nothing to start. You need the system matrices. I can explain how to get them. But very efficient to implement, linear time. It starts working right away, right? There's no pre-computing like LQR. I don't need to kind of solve ahead of time or anything like that. I can go I can update as I go along. Okay.
Clarification, the
Yes.
cost function is being provided.
Sorry?
In what form? Are you getting the full cost function or just the cost values?
Aha, great question. I will repeat for the people at home. The question was, how is the cost function provided? The algorithm itself, all it needs is the gradient of the cost function as a function of M. Okay. Now, any representation that allows you that is sufficient. If you have an LQR, so you know the matrices R and Q, you can of course compute that. If any explicit function, you can compute it. What happens if it's not explicit function? Let's say you can only see the cost. Let's say so. That's a challenging thing that in optimal control you don't know how to do. But luckily here we can use something called the bandit convex optimization or zero order optimization. What you do, you make a small perturbation over the M, and take the value of the function there, and the value multiplied by the direction of perturbation is a random variable whose expectation is the gradient. Bottom line, you can create, with just the value, you can still create a gradient estimator. Yeah. So yeah, so this is very robust. There are many ways you can change this. You know the function, you know only the value of the function, so various things you can do here, and it will give you the same type of bound. So if you only know the value itself rather than the full gradient, the regret bound will suffer the fact of the dimension, which is unavoidable.
I have a question.
Yes, please.
So if you're going to assume that your control policies are linear, the form of with theory X, why not emphasize an effort to update K and learn K
Okay.
as a
Good.
function of noise?
Good
Then
question.
you can calculate gradients of your cost function with respect to K, take advantage of perturbation analysis theory and so on.
Yes. Okay. Good. The question was, why don't I update K directly? Okay. Just a small note. This K here is a stabilizing controller. It's not an optimal controller to the code, stabilizing the system. And the question is, why can't I take gradient over K to make that optimal? And the answer is the following, if I go back a couple of slides. So if you look at the control as a function of K, it has this nasty polynomial shape. Now you can say, wait a minute, why do I care? Well, if I plug that into the cost function, this is a highly non-convex function of the function of K. So I can run gradient update, but it will not get me to optima. I'll be stuck at the local minimum because it's not convex. Okay. And you can try it out and it will fail. So this is a real problem. It's not just an analysis problem. Yeah, great question. Yeah.
Does this mean that your cost should be smooth and convex, I suppose?
Yes. Smooth doesn't have to be. Convex, yes. Doesn't have to be smooth because all the gradient descent thing that I had in the slide before and I kind of skimmed over, that works with the subgradient, even if your function is non-smooth. And even non-differentiable in some measure of 0 points or whatever. It's very robust. So convex, yes, has to be convex, but can be non-smooth, and that's actually very important because piecewise linear is a very important class of function. What does have to be smooth, and that is, go back to this slide. So this relates to the question I had from the back here. I linearized the system, right? The dynamical system, Lyapunov. So for Lyapunov linearization method to work, you need smoothness of the dynamics. That doesn't have to be convex, only smooth. Yeah.
Does this tab metrics are stable? Like, does it have physical meaning of this tab?
Can you repeat? I didn't hear.
Yeah, I mean, for the tab matrices there, when it's stable, like it's like the color, does it has a physical meaning for tab?
Yeah, great question. The question is, do the M matrices have a physical meaning in terms of stabilizability? I don't know. I mean, I don't think so. But I honestly just don't know. I'm guessing that the answer is no. So what happens is, again, I will go to this analogy of the Lasso sparse prediction problem. When you have a sparse prediction problem, trying to find the sparse confounding factors for a regression problem, that might have a physical meaning. But guess what? It's NP hard to find, right? Now we do an L1 relaxation, we solve the Lasso. Does this have a physical meaning? No, it has no meaning at all. But we know it's, in terms of prediction, it's as good as these sparse points. Same thing happens here. So in terms of control, this is going to be as good as the best minimum policy, even though it might have no meaning at all, and maybe finding the best case NP hard and so on. Okay. So we lose interpretability, we lose some succinctness in formulation, but we gain the convexity, the ability to optimize quickly. Any other questions? Yeah.
Sorry. Does this mean that, like, as part of the noise, you are also trying to add the nonlinearity that you lost through the linearization part, or that one included?
Okay, that's kind of, the question is whether the noises contain what we lost in the linearization. Theory says no, because I guess Ashok was asking me this earlier in the day. If the perturbations depend on the state, the guarantee still holds, by the way, the regret guarantee is correct, root regret, and it's deterministic and doesn't depend on anything. But it becomes a bit mute because had I chosen a different controller, I would have been in a different place in space and so on. So it becomes counterfactual. I don't know how to deal with that. But on the other hand, I do know that this is meaningful in many interesting situations. For example, if I fly my drone in some bad weather or good weather, the weather doesn't depend on what I did. Right? It's some absolute thing that the God decides, or I don't know what decides. So that does not depend on my controller. Therefore, the perturbations are given by nature. It's an okay assumption to make. Similarly, I can give you other examples. You play the stock market. If I'm not a huge player in the stock market, my actions do not affect how the market behaves. And therefore, whatever noises or perturbations you see are not an effect of my actions. Okay, so it's a reasonable assumption to make in many situations, not always. It's not always reasonable, but many situations it is. Yeah. Okay, thanks. Great questions. Anything else, or I'll move on? Okay. Good. So here is some demonstrations of the system, and I will start with just simulation. Oh, I see I need to end soon. So I'll start with just simulation and then tell you a little bit about follow-up works. So this simulation, we implemented the gradient controller and compared it to LQR. And this is just sanity check when you have Gaussian perturbations. Of course, you can't expect it to do any better than LQR because LQR is optimal. It will, by the way, converge to it if we take more iterations. Now, if you change the loss to be L1 rather than L2, already the red line, which is the gradient controller, does much better, can achieve a much lower minimum. If you have a random walk, so your noises are time dependent, okay, then then LQR now becomes worse. The black line is the optimal solution which you can solve. You can solve the Riccati equation here too. This is a positive demonstration that the gradient controller reaches that one, even though it's still not so difficult that we can compute the optimal. We can compute the optimal, but we still reach it. And now this shows you like sinusoidal noise. You cannot compute the optimal control. I don't know how to compute the optimal controller here. It's too hard. And the LQR now is miserable in terms of average cost compared to the gradient-based method. And you may tell me, wait a minute, what if I use robust? Well, robust is like all the way up here. So 2 orders of magnitude worse. This is a logarithmic scale. So no control at all is this yellow line, which just exploits the system completely. Good. So I covered the basic paradigm and simple gradient controller. Let me mention a few extensions, and then I will conclude and have time for a few questions. Good. So extension 1. I wonder if I have internet here. Okay. I wish I had the video. So we can invert a pendulum, which is a nonlinear dynamical system, using this method. And even compared to ILQR, which is a planning method, so iterative linear control, you kind of iterative linearized plan, iterative linearized plan. It still does much better. I wish I could show the video, but I will post it online. This is another demonstration. So here, we try to fly a drone from source to destination. And there is some wind field, some unknown wind field here. And the comparison is again ILQR. So ILQR is a planning method that iteratively linearizes the model and does an optimal planner and executes a control and does it again and again. This is model predictive control. What we have here is that when the noise is large, which is here, so when the wind is very large, the gradient controller does much better than ILQR. Okay. maybe I wonder if I have. Yeah. So let me so let me just conclude, and then if there are questions, I'll take them. So there are some textbooks that I've posted here for people that want to take a closer look at this and extensions. And we have a library of code that's written in JAX. JAX is a language that is differentiable, allows you differential programming. So generally, my thesis was, and a little bit still is, that whenever you can differentiate through the environment, you can take gradient steps and optimize your policy if you have the correct parameterization. And this can go way beyond just linear systems, right? So you can linearize any smooth system, and hopefully whenever you have accurate gradients. So this is a software library that allows you to take gradients very efficiently through the dynamics. And let me just summarize what we've seen. So I talked about control versus RL, and the power of control that you can differentiate through the environment, which you cannot do in reinforcement learning, but it's a very verbose statement of states and actions and inefficient in some way. And that allows you to obtain efficient algorithms sometimes. I motivated robust methods and talked about online convex optimization and how to use that power with convex relaxation to derive the gradient controller. And I put here some more resources. I did not discuss what happens when we have the system unknown, partial observation, and so on. And I'm happy to do it if you guys ask me questions now. But I will end now for those people that want to leave and happy to take more questions. Thank you.
So, can I ask a question? Can you hear me?
Yes.
Okay, I'm out in cyberspace. We had a pleasant lunch together today. So I missed something at the very beginning. Is you passed from a fairly general dynamical system to a linearization, and I'm if you do Jacobian linearization, it has to be linearization about something, about an operating point or about a trajectory or something. How does this work?
Exactly like you said. So it has to be around given dynamics. You need to know the dynamics. You need to be able to take Jacobians. And if you don't, then this is mute. This is not correct what I wrote. So I'm assuming the technique that I presented works for time-varying linear dynamical systems. They do not work for more complicated dynamical systems. They only work for whenever you can do the Lyapunov linearization. Which, as you said, only works in certain situations. Yeah.
Okay.
Beyond that. Yeah.
Okay. Thank you.
You're very welcome.
There is in the chat question.
Let me give priority to the people here. Ashok, yeah.
You mentioned at the beginning that maybe there'd be some people about adapting to the amount of noise, something like that. Like, I could see empirically, right? Yeah, I'm going to presume we could do better if say W was 0 or something like that. Right? Is there a theoretical result of that nature?
You're asking if the noise behaves in a certain way.
Yeah, like if let's say there's no perturbation, actually this would be much better.
Right.
If there's a lot of perturbation.
Right. I see. Okay. Just the regret definition itself compares to the best controller for the particular noise sequence that has been observed. Okay, so the states and the costs are contained within them in some sense the noise sequence, right? So that's what I mean. So no, the regret bound will be the same regret bound, but the point being that you compete with the best controller for the particular action sequence, noise sequence that you have seen. Just like in standard offline, online convex optimization or online learning, you compete with best decision for the particular cost function that you have seen. Right? So you have regret, it's a per instance. This is something kind of I thought about again when I kind of did this work, like it's pretty magical, right? So in online learning, we compete with the best decision for the particular noise functions that happen, which is a stronger notion than all functions, all noises, random sequences, and so on. Yes.
Wasn't the M multiplied by this the sequence of M?
It is, yeah. That's the controller.
0.
You're asking why is the control not 0 always?
Yeah.
Okay.
It's
Yeah. So if the noises are all 0, I'm assuming I have a stabilizing controller. The system will go to 0. So I don't need to do anything. Just go to 0 very rapidly. But in order to capture costs that have an offset, for example, then you need to add an additional, so either a W, which is always 1, or just add a constant that you also optimize in the controller itself. Yeah, good question. Yes?
Is there a way to extend the framework with constraints of the environment and potentially this constraint might be unconvex?
Excellent. Thank you, Ahmed, right?
Yeah.
So Ahmed asks, can we add constraints here? And the nice thing about this formulation is that I don't know how to handle non-convex constraints, but any constraint that is convex in the states you can add, because you can you have a linear transformation between the states and the perturbations, and you can equivalently write the constraints in the perturbation space. And now you can just run online convex optimization with this added constraints. So that you can do. That is actually the motivation behind, if people here heard about a system level synthesis, that is something came out of Doyle group. It's very similar formulation to this, but I mean, at least the noise kind of formulated transform, but they have noise, there's some similarities, but their motivation was to have constraints in a convex way. So that same thing applies here too. Yes?
Can this be extended to like for like a zero-sum game or like specific to where like the noise can be like adversarial agent?
Yeah.
And have you tried that already?
Oh, okay, great question. So actually, one of my students, Uday, looked at the problem of, can we, given a dynamical system, can we, or a controller, can we find the best, the kind of most adversarial perturbation sequence for the controller? And turns out that has a very similar formulation. You want to maximize instead of minimize. But when we have quadratic costs, we know how to maximize quadratics. That's like an eigenvalue problem. And you can solve a very similar formulation to this one and find, for any controller, you can find the worst noises that will make it unstable or kind of, so it's useful for verification, yeah. But this is the only work I know in that area that has some kind of provable guarantees, and I think it's still wide open because even that there are issues of dynamic equilibrium that arise that are unresolved. So there is a lot of open questions in the multi-agent setting for this type of problems.
So does that mean that you don't converge to like double optima or like the? But like,
yes.
Do you reach Nash equilibrium or like that?
We don't know how to say that you reach Nash equilibrium. You reach some form of solution, but what you would like to say is that you would like a Nash equilibrium. Like for whatever strategy the controller is playing, I play optimal, and it's not worth it for them to deviate, right? We cannot say something so strong. So it gets a bit technical. I don't want to spell everything out here, but there are questions with convergence to equilibrium in that setting. Definitely. Interesting questions, yeah. And now there is something online, maybe? Oh, yeah. So is the state xt determined based on M or M1 to T? The state is determined based on M1 to T, but it is epsilon approximated based on M1 to H, where H is logarithmic in the approximation guarantee. So you have a very, very good approximation if you take finitely many elements. I hope this answers your question. Any other questions? Good, thank you very much.